Hello, my name is Georgios Katsaros. I'm working at the Institute of Science and Technology Austria, and today I'm going to speak about germanium qubits, multispin encodings. Let's start with the physics of holes. When we are at university and we take a semiconductor physics course, we learn about the energy diagram of a semiconductor, and we typically learn about the conduction band and the valence band. So what is the difference between electrons and holes? So this is the valence band, this is the conduction band. If you write down the Hamiltonian for electrons, you will see that it is rather simple, and that the direction of motion depicted here with a black arrow does not correlate with the spin degree of freedom. The situation is much more complex when you think about holes. So you can see that the Hamiltonian, which is the Latin-Zircon Hamiltonian written for germanium, is much more complex. And what are the consequences of this? Let's first recall that when we speak about holes, we have heavy holes and we have light holes. So heavy holes have J equal 3/2, and the projection Jz can be plus minus 3/2, while for light holes, we again have 3/2, and this time we have a projection of plus minus 1/2. If you now hit the Hamiltonian on a heavy hole or a light hole state, what you will find out is that effectively the pseudo spin points in the same direction of motion when we are in bulk. And interestingly, if you act with the Hamiltonian on a heavy hole state, after a few simple steps in math, you find out that the heavy hole mass is given by the effective mass divided by gamma 1 minus 2 gamma s, while if you act with the Hamiltonian on a light hole state, you will see that the light hole mass is now the effective mass divided by gamma 1 plus 2 gamma. So it means that the light hole states have a lighter mass than heavy hole states. That's why the name is also like it is. Things become even more interesting the moment that you apply a confinement potential. So let's now imagine that we are going to put a confinement in the z direction. So we will create a two-dimensional hole gas. So if we now see what the confinement does, the confinement effectively has as an influence that now the pseudo spin looks in the z direction. And that is because our k vector kz is much smaller than kx and ky. So what is the consequence of this? If now you hit with the Hamiltonian on a heavy hole state or on a light hole state, again, if you do the math, now you will see that actually the heavy hole mass is lighter than the light hole mass. So how does that look like in an energy diagram, in the energy dispersion picture? So heavy holes and light holes have now a different mass. So they split in energy, and the heavy holes have a light mass, the light holes have a heavy mass, and when they meet, you get an avoided crossing. So let's now try to understand what is a hole spin qubit. When we think about an electron spin qubit, it's actually very easy, very intuitive. You put an electron in a magnetic field. There is the Zeeman splitting, so you have the spin up state and the spin down state. So with projection Sz minus 1/2 or Sz plus 1/2. If you think about a hole spin qubit, we saw that the lowest in energy state are heavy hole states. So I think then of a heavy hole Kramer's doublet, so a hole spin qubit, but now we don't think of a spin, but we think of a pseudo spin. So now we have Jz plus minus 3/2. And finally, if we want to think further about the whole wave function, now the whole wave function is nothing else than a superposition of the spin up and spin down states entangled with the orbital degrees of freedom.